which is solutions, concentration and molarity. So if you had a look at the questions that we've already done, you would have noticed that we're talking about the gases or masses of solids that we're reacting. But there's a whole lot of chemistry that involves solutions. And those of you who did the titration competition would know that we can do these reactions in solution, and we can also calculate quantities for solutions. So what is a solution? I'm using this word assuming that you understand what I mean. What's a solution?
When a substance is dissolved in water or another.
So we have a substance
Solvent.
dissolved in something. That's right. For our chemistry and for chemistry in chemistry 4, the something would always be water. Our solutions are all aqueous solutions, so we're dissolving things in water. And do you remember what the words were? So the dissolving in the something, this is actually the solvent. I don't know if any of you have heard about the solvents used in dry cleaning and that sort of thing, that they don't actually use water, so they're using other organic compounds. And this is the solute. And then when we form them together, we form a solution. So this means that we're interested in substances in solution. So we dissolve something and we've decided that it's always going to be dissolved in water. And then we can perform chemical reactions. One important part of dissolving things, just say I have a beaker here and I've got a pile of, well, it can be like sodium chloride. So I've just got a beaker and I tipped in like a quarter of a cup of sodium chloride. What's going to happen?
Dissolve.
It'll start to dissolve, yeah. So we'll end up with sodium ions, chloride ions in solution. But what about how it's distributed? How will these ions be distributed?
In between the hydrogen molecules.
I'm thinking about the beaker itself. Is it going to be random? So if I just tip this in and it's made a little pile at the bottom of my beaker, I haven't done anything else to it. So my sodium chloride will start to dissolve, but I want you to tell me about the distribution within the water. Any idea of what's going to happen? Doesn't sound like it. In actual fact, we're going to have a much greater concentration closer to the pile of the sodium chloride there. What I've got is an uneven distribution. So I've got, at the top here, I've got low, and I'm going to use this word concentration, and high concentration down the bottom. What do I need to do to change that? How could I make it uniform? Yeah, so we're going to, if we mix it all up, okay, so we mix, then we're going to have an even distribution. have a word for this when it's all evenly mixed throughout our solution. It's homogeneous or homogeneous, depending on how you want to pronounce it. But the homo meaning one kind of distribution rather than multi. So you might strike this word, and that's what its meaning is, that we've got an even distribution of our ions within solution. Now, this is for an ionic substance. When we dissolve it in water, our ions separate, don't they? If it's soluble, it's the ions that separate. But if it's for a covalently bonded, can't spell. And the example in our book is sugar. If I do the same thing and I put some sugar in here, what I end up with are just the sugar molecules separated. And so if I put electrodes into this solution here, and I try to, I can electrolyze it, or if I wanted to measure whether it was able to conduct or not, this is going to be a good conductor of electricity because of the presence of those ions in solution. If I do the same thing here with my covalent solution, then it's not going to conduct as well. It's actually going to be a poor conductor. Okay, because these are molecules that aren't, they're not ions, and so we need charge carriers. We do know that water is a polar molecule, don't we? And so this end is slightly negative, and the hydrogen ends are slightly positive. But again, this is not as big a charge as is present on ions, and so it's not going to be as good at transferring charge. Now, what's happening here in a little bit more detail with our salts. So for our soluble salts, if I put some sodium chloride in this beaker, it will dissolve, and what that means, or what is happening, is that the chloride ion is actually more attracted to the hydrogen of the water molecule than it is attracted to the sodium ion. And the sodium ion is way more attracted to the oxygen end of the water molecule than it is to the chloride ion. And that's why they separate. It's sort of like a second marriage. Worked out all right as a solid, end up in the solution. No, we're going to change now. We actually prefer these other charges, and so those ones will dissolve. There are, as we know, some insoluble salts, and they are insoluble because their attraction to each other is much stronger. So, for example, barium sulfate is not going to pull apart because the attraction here between the barium ions and the sulfate ions is greater than the attraction between the barium and the oxygen end of the molecule and the sulfate and the hydrogen end of the molecule. Okay, so that's what's happening when we dissolve. Now, there's a bit of information on page 39 about concentrations and the different ways that you can measure concentration. So I used the term concentration up here, and I said that this was a low concentration and here this was a high concentration. Concentration is all about how much stuff Stuff is a highly technical term, but we can use this because it's a quantity of stuff. If I have a lot of stuff, it's going to be a high concentration. If I don't have much stuff, it's going to be a low concentration, and it could be anything. Okay, so it's all about quantities, and it's therefore related to moles, because moles is also about how much stuff, isn't it? We have a formula that we use where concentration is capital C here, concentration. You're also already very familiar that N is what we the letter we use to represent moles, and here V is volume. The units moles per litre for concentration, and moles is obviously measured in moles, and the volume is measured in litres. And if you look at the units, it makes sense that concentration is moles per litre, because what we're doing here is we're dividing moles by litres, which is moles per litre. This is the most common way of being asked questions as far as concentrations are concerned in chemistry. And the reason why the volume is an important part of determining the concentration is because if I have 5 moles, say, and I'm going to represent that with 5 circles, concentration is going to be very different if I have a different volume. So this one here with the smaller volume is going to have a much higher concentration than the one with the larger volume. The other relatively common way of expressing concentration could be in grams per litre. This one's actually really easy to calculate because most of our calculations start out with grams, or we go through our masses with our calculations anyway. And so it's not difficult, although sometimes students find it difficult because when 99% of your calculations are moles per litre, when you struck that grams per litre line, you think, hang on a minute, I've forgotten how to do that. But it's not very difficult. You just need to work out the mass that will be present. Now, there's one more thing, or another thing I want to talk to you about solutions. Is if we just say I have a beaker here and it has 100 mils of water. Now I'm going to add, I'm going to add 15 grams. I'm going to add 15 grams of copper sulfate. Now we all know it's going to be copper sulfate pentahydrate because that's what we have available. We're just going to call it copper sulfate. What's happened to my volume? Well, you'd think so, wouldn't you? But in actual fact, with a relatively high volume of water and a relatively low mass of whatever it is that you're dissolving into your water, the volume will remain the same. So don't get hung up on masses going into volumes and trying to figure out, well, you know, if that's 15 grams and surely this has gone up by 15 mils, that doesn't actually happen. The volume's going to remain the same.
But if it was sand, the volume would increase because it's not.
It's not going into solution. It's not dissolving. So that the volume of water wouldn't change. It just means that you've displaced some of the water up.
But the total volume taken up in the beaker would
But
increase.
the total volume in the beaker, like the level measured on the side of the beaker, increases. If I'm dissolving my copper sulfate in water, what happens is the ions fit into the gaps between the water molecules. And so in essence, we now have a solution that has the 15 grams of copper sulfate dissolved, and it's still 100